In this video, we will discuss how computational fluid dynamics, or CFD, actually works. In fact, this subject is generally very complicated due to its mathematical language and computational methodology. But I try to make the explanation as simple and as intuitive as possible. Although for daily use simple case of commercial CFD software, you might not need a deep understanding of CFD theory, but the knowledge of how CFD actually works helps you much to determine which setting you must use in your simulation and helps you faster the troubleshooting process in case your simulation are going wrong. Well, talk about fluid dynamics problem, we should first discuss the basic law of fluid mechanics, which is the basic law of physics. They are the conservation of mass or continuity, the conservation of momentum or Navier-Stokes equations, and the conservation of energy, which is generally refers to thermal energy in CFD. First, the continuity equation states that the mass flow rate goes into a control volume will always equal to mass flow rate goes out from a control volume plus the mass rate of change in that control volume. For example, if we have a bathtub with its faucet opens and have a flow with 100 grams of water per second, and the bottom sink is also opens and make a 20 gram of water per second, we can calculate the rate of change of water in the bathtub is 80 gram per second. As shown here, the rate equations are the differential and integral equation of general continuity equation, which are sometimes unpractical to solve it for complex flow. Or maybe the black equation you might be familiar with is the form of continuity equation for steady state flow with certain flow direction and cross-sectional area. Okay. Secondly, this is one of the unsolvable important mathematical problem, the Navier-Stokes equation. You can solve this equation analytically and get $1 million prize from Clay Mathematical Institute, but most people prefer to solve it numerically because of its nature of nonlinear partial differential equations which not always have a unique solution. This equation basically derived from second law of Newton's force equation. Force is equal to mass times acceleration, or force is the rate of change of momentum. In fluid problem, the typical force is pressure from the system, frictional force from viscosity, for example, or maybe the gravity from its weight. The rate equation shown here is the Navier-Stokes equation in the form of vector partial differential equation, and the black equation here is the form of Navier-Stokes equation with steady state, non-viscous, and one-dimensional, or we known as the Bernoulli equation. Okay, in classical mechanics, energy equation or conservation of energy often refer to conservation of mechanical energy, which is kinetic energy plus gravity potential energy is always constant. On the other hand, for fluid mechanics, or specifically in computational fluid dynamics, energy equation often refer to thermal energy, the temperature. With computational fluid dynamics, we can model all the heat transfer nodes from conduction, convection, or even radiation. Now, let's examine a simple fluid flow problem and solve it with analytical method. I even bold and color red the simple text to emphasize how simple is our case. Let's assume we have a pipe with diameter d and we want to know the velocity distribution along the radius. As we can see, our simple problem needs a lot of mathematical effort to obtain the solution. Now, we add a little complexity to our problem. For example, let's put a ball inside this pipe. Any idea how to solve this problem? This problem is become very complex and hard to solve mathematically or analytically. Maybe you can solve this problem if you are very good at math, but it will take a tremendous effort and not worth compared to the solution obtained. Moreover, if the flow becomes turbulent, this problem often impossible to be done analytically. Now, how to solve this problem? This is one alternative to get the solution. Instead of solving the equation in the whole domain instantaneously, we can divide our problem into small segments with simpler volume or elements which are simpler to solve analytically. This process is called discretization or meshing. The idea is to convert continuous domain which has continuous mathematical properties to be a discrete domain which has discrete mathematical properties. The consequence of this idea is converting continuous differential integral equation into discrete algebraic equation, and we can solve it numerically. This is also known as numerical method. And commonly used numerical method in computational fluid dynamics is finite volume method. By the way, the equation used in this slide is just an oversimplified finite difference method to illustrate the idea. Okay, now we can solve the equation. It is the end of the story? Unfortunately, no. The idea of dividing a continuous domain into many domains also makes the number of equations to solve be a lot. This is very tedious task and time consuming to be done analytically, or at least for a normal human being. So, we need something which can solve this problem faster, much faster. And the best idea to handle this task is using computer. This is maybe obvious for nowadays computer, but not for the early development of CFD, when the computer is very costly and much less powerful than today. Imagine with 1 GHz of processor, for instance, we can do 1 million of calculations or processing in every single second, which is much faster than normal human being can do. Finally, this is the colorful part of our process and paid off our struggle to step up and understand our problem or our simulation. This is called the post-processing step. In this step, we compile our solution data obtained from the numerical calculation which previously done, such as velocity, pressure, temperature, or the other flow parameters, and plot it in each element of the domain in the form of color, or maybe the graph. So we can interpret the data easily, intuitively, and beautifully. Well, to summarize our discussion about how CFD works, we can express it into a sentence which I refer from the Anderson's CFD book. CFD is the art of replacing the integrals or the partial derivatives in these equations with discrete algebraic forms, which in turn are solved to obtain numbers for the flow field values at discrete points in the time and or space. Okay, this is the end of our video. I hope you enjoy it. To get more insight about computational fluid dynamics and discuss more topics about it, stay tuned in this channel and please visit our website at ironengineering.co.id. Okay, thanks for watching.